So next up, we're going to be looking at UEFI. And for those that are unaware, UEFI is essentially like the new version of BIOS. And it is essentially the component that sits between the hardware and the operating system. Now, there isn't a lot of kind of threats that are available or that have been observed in UEFI. And you can see this graphic that I just put up on the screen is from a TrustWave article that lists kind of the history of EFI threats. But the reason why I think it's interesting now, in that very recently, and you can see on the screen here, the end of 2022, BlackLotus hit the scene. And BlackLotus is actually available on the dark web, and it's been open source. So I think we'll see more of this type of threat as we move ahead. Microsoft has also been a bit slack in the past, revoking various EFI loader files and doing the security on UEFI. And it's kind of interesting, the project bootloaders.io is starting to also make it a little bit popular. And well, this is what got my attention to EFI and made me want to kind of dig a bit deeper. But I think it's important to understand the visibility, and that's what this lab is going to do. So first of all, about UEFI, what we're mostly interested in is persistence. There's two main parts that are relevant here. One is called SPI, or Serial Peripheral Interface. And this part is the firmware component. The caveats to this kind of persistence is it's very difficult to implement and detect. Because it's hardware, there's essentially risk of bricking the machine if someone messes with it. So it's typically your very high-end kind of malware. And even to get at it as a defender, I'm going to show you some visibility to see some components that are stored in the SPI, but it's very difficult to get to where you need to dump the firmware off and then review it with special tools and things. So we're not going to be focusing on that. Instead, we're going to be focusing on the visibility that's available, and also the second type of persistence, which is called EFI System Partition, or ESP. In this case, all you need to do is bypass secure boot, so bypass Windows like checks and validation of your EFI boot process, and then you can use it and get on the machine to persist. Of course, the first is much harder to implement and also harder to detect. The SPI type persistence will persist across even formats because it's on the hardware itself, while ESP is a separate partition. So when you format the machine, you'll actually format over the top of any persistence that you have in the ESP partition too. So what we're going to do in this exercise, while the last exercise we looked at kind of a MITRE entry and we kind of kicked off a few detection use cases from there, in this exercise, we're going to walk through a really great Microsoft blog on BlackLotus. And I'm going to be installing a copy of BlackLotus, and then we're going to show the visibility and show detection on that. So some of the opportunities you can see here are listed, but we'll walk through them in a bit more detail in the lab. So that's the lab. Here is the lab for BlackLotus that I've developed for UEFI visibility. What we're going to do here is essentially look at our EFI visibility built into Velociraptor currently. We're then going to install BlackLotus and then walk through the detection use cases from the Microsoft article. Now, the Microsoft article is pretty thorough in in what it looks for. And it's kind of a use case that you do this kind of stuff normally in real life. So I thought it was a really great use case for us to kind of show how I would approach things in Velociraptor. During here, I've actually built on some of the accessor use cases. Okay, so first of all, I just wanted to touch on this enabling UEFI on virtual machines as well. I'm not going to walk through this part, but obviously to do the lab, you need to have UEFI enabled. Now, what you might find is if you haven't set up UEFI before, you'll find you'll get an error like you're seeing on the screen here. And that's because you probably haven't got the prerequisites enabled, these three things. Now, if you're running Windows, there's a link here that will kind of give you what you need and it will step you through. Otherwise, if you're running Mac, you should be able to find these things. And I've added some screenshots of my config to get you to the right place. Okay, so first of all, let's walk through EFI visibility. So again, we need to do the whole running GUI mode. So essentially the EFI visibility was written in by a user, a couple of plugins and functions a little while ago. And essentially it's relying on a couple of undocumented APIs in Windows to extract the appropriate EFI data. And it works pretty well. What its challenges are is it is incomplete data. So the task we have in this first lab is to just take a look at like what's available. So when I bounce through all of these steps to get to my notebook, and I've just created a notebook here. It's actually called EFI variables, and you can see I'm using the helper function again. So we select that and do question mark, and we can see the plugin arguments. So we can specify name or namespace. And I'll just run this without. I think that's what we do in the lab as well. And you can see a whole bunch of parameters are here. Probably means nothing to you, but you'll see a bit later where they come in handy. But to actually get the values out, we hit value, and that's actually a Boolean. You just put yes, and you can kind of see the values are binary. Now, this is not all the components that are on the SPI. The bits that are relevant are actually in the artifact. So let me just do a search for it first, and we'll just EFI, and here it is. So generic system EFI signatures is the artifact, and this is actually copied from a chipset project that essentially, I think this project is designed to run and parse EFI data. What it's doing is essentially it's just taking some of those binary fields, some of those binary values, and it's parsing out the signature data, right? Signature and certificates, this thing does. And this is actually really handy when you think about how Velociraptor works. So when we run this, if we type in, what was it, EFI, is generic EFI signatures. Now, there's not a really great description here, but it collects EFI signature information from the client. In terms of parameters, there's no parameters, and it's pretty fast to run. The thing I didn't mention is it is a generic artifact, so it is compatible in Linux and Windows in the current version. Like if you look at the source code in Velociraptor for this, the Mac OS there is no code for that, so it won't work on Mac OS. But for Linux and Windows, it works. And when you look at the results, you can see we have a DB and certificate information. So it's extracting the certificates in UEFI. But then it also has the DBX hashes. So you might be thinking, what is a DBX? A DBX is essentially the revocation list. So what has been revoked and the hash is there. So a lot of the like EFI, like BlackLotus, for instance, it works by essentially exploiting vulnerable bootloaders. And what Microsoft was really bad at was updating this revoked list of things. What they have done now is obviously they've updated it, so it's a lot better. But one of the problems in EFI is there's like a storage constraint. And this is actually one of the reasons why I wanted to look at EFI visibility in Velociraptor, because with BlackLotus going open source and there being these constraints around what they can actually detect on, my assumption was we're going to see more of these threats as we move ahead using these persistence methods, because the cost of acquiring them and executing them has come down significantly. Okay, so the next section, we need to actually install BlackLotus. So I can show you some of the visibility. Now, the results are pretty straightforward to do this. I have a PS1 file sitting on my gist again that will kind of run BlackLotus. But what it's doing, I've got it open here, is we're essentially determining a payload, adding exclusions into Defender. So if you'd like, or if you'd prefer, maybe if you have any issues, you can disable Defender a better way. But this should do the job. In my testing, it worked. And then what I'm doing is I have a base 64 encoded BlackLotus that then drops to disk the payload name and then loads it. So really simple stuff. And this is just to generate data and show you some of our visibility. We're not doing any amazing like memory-based detection or telemetry or anything like that. We're mainly interested in the disk artifacts, so we can cover off that second persistence type that I was referencing. You just need to copy this and open up PowerShell ISE. And remember to run as admin. You might get a Defender warning telling you that it's been disabled or something. But you'll know it's successful when you can see the file on the desktop. And there it is. Cool. I think in the instructions, I have a reboot after the install. And the reason for that is TCG logs essentially are logs that the OS updates the boot process. So we're just going to reboot now. And I'll probably pause the video and we'll be back when it's finished. So we're back after the reboot, and I've just loaded Velociraptor and PowerShell ISE. And what I'm going to do is just mess with the preferences for Defender, and we'll see if it fails. Boom. Okay, so we know it's successful here. And the reason for that is one thing that BlackLotus does is it messes with the token privileges of Defender. It's a really cool way of taking out AV and still keeping the service running. So any checks, the AV is still running according to the services. Okay, so the first thing we're going to do is query the EFI system partition. And if you have a look at the Microsoft article, they reference looking at timestamps in the EFI system partition. So we're going to open Velociraptor and run exchange UEFI. Now, Mike actually added in a fat accessor into Velociraptor in version 7. And I actually didn't get a chance to put this artifact in. But what this artifact does is it takes an input of the physical drive. It takes the sector size of the drive and then a glob. And this is a really cool expansion of our accessors. What we do here is look at the partition table, and maybe I'll go back and show you the partition table. And what the partition table does is, again, it takes an image path, and we just pass that through a sector size, and it uses our binary parser to parse out the relevant partitions in an MBR or a GPT header. So in this case, we're looking at a GPT because it's a UEFI disk. But what's really cool about this is if we come down to here, it's using an accessor called raw file. I actually didn't get a chance to add a lab on this in the accessor section, but by using this path spec and specifying the raw file, you can see we're accessing it with an offset accessor, which then means we can parse that disk. That becomes super interesting if you're doing things like hunting the MBR. It also opens us up to things like carving in the future, and not relying on files. And these are kind of use cases that I just haven't had a time to add to Velociraptor yet, but it's a really interesting capability in that we can use this raw file accessor to effectively treat a disk as a file with the offset accessor. Hopefully that makes sense. And like, if anyone has any questions on how that works, ask some questions in the Slack channel, and I'll drop in maybe some answers or maybe some small little examples that you can test with. When I've played with this stuff, typically what I'll do is I'll just access the bytes and then I'll just output the hex. And I've done stuff like just dumping the MBR off a box and taken a look at it and then compared it with forensic tools. And it's exactly the same. It's really cool when you look at it. Okay, so we've got the EFI. Windows Forensics UEFI. And that artifact is looking at a glob of EFI. So again, we'll come down here. You can see what we're doing is, after parsing out the partitions, we are then using that same raw file method and then passing it to the fat accessor. The reason for that is the EFI partition is a fat partition. So what this enables us to do is use a glob. It then parses the files that are on fat, and then we can query them. So that's a really long roundabout way of saying I can now run glob over fat partitions. When I run this, you'll see what I mean. So you can see we've had 12 results come back. And when I click on the results, you can see the kind of stuff we're parsing. Now, this is quite small. Maybe I'll make it, that doesn't help too much. Coming to notebook, let's target here. Now this is a little bit easier to see. So you can see we have the timestamp up here is about now when I'm recording this, whilst the other timestamps are when I installed the OS. You can also see there are deleted items with the timestamp the same. So this is really suspicious considering, you know, you may not have done an update or an install of the OS at those times. And you can also see the System32 entry here, which the System32 folder should not exist on the EFI partition. So the other thing you can do if you wanted to see everything on the disk, you could just run that blob, and the EFI partition is small enough to kind of allow you to do that. So just copy these to get a better view. And you can see here, we've got the System32 folder. It has the timestamps that are relevant. And bouncing down, you can get an idea of what's there. Now, in the lab, I think we specifically query the System32 folder, but let's just do where System32, and just to reiterate, like there is no System32 on a usual UEFI drive. Now, what you can see here is we've output all the items in that System32 folder, and you can see there are some that are, well, they're all deleted, but the System32 folder has not been deleted. If you have a look in the guide, I think I included a picture of the publicly available, down here. So this is a picture of the baton drop exploit that's publicly available. And baton drop is essentially what BlackLotus used to bypass secure boot, right? Now, out of all the samples that I found of BlackLotus, this one that's running here is the only one that seemed to work. And that's why this installer is so big, in that it actually has the EFI driver included, embedded in here, and it runs. So it's like a 2.5 meg file opposed to like 100 kilobytes or something like that. But for me, this is a really awesome validation of this use case, to be able to query the EFI. And even something like, technically you could data stack this, but just hunting for suspicious strings, or even doing like a not query, saying anything that's not the EFI. I think the other thing I wanted to look at is if we expand out first, and then we'll add. Yeah. So let's add Authenticode and PE info. We'll add data magic too. And we'll do OS path. B time. M time. We just get some metadata around the PE information, right? So yeah, the folder you're not going to have much, but you can see like these are really suspicious, even if you didn't know that it was bat and drop. What I wanted to show, if we go back to this section, you can see some of these EFI files. And that one looks legit, that looks legit, but then this guy here is the known BlackLotus certificate. So we could add a hunt for that. What I'm trying to show is the visibility that we have now available to us in Velociraptor. Okay, so the next thing we're going to look at is essentially the same use case, but we're going to focus on adding Yara into the mix as well. All right, so when we come back to our Velociraptor GUI, hit plus, UEFI, and we've got a new detection.yara.uefi artifact. This does exactly the same thing as the last artifact, but it rolls the file results into Yara, like we worked through with some of the other accessor use cases and some of the other things we've been running. By default, we have the BlackLotus Yara rule that is on Malpedia. I might add a few more when I get some time and add this into the main repo. But like I said, it runs exactly the same way. So when we run that, it will go off and it will parse the partition table, find the EFI partition, and boom, there we go. It's got the hit, which is really handy. The next component we're going to cover off is the measured boot logs. And the measured boot logs are located in this location here. They're kind of interesting because they're just a log file. You think, oh, I'll just take a look at them, but they're actually a binary format. And there's a few tools that can parse the binary format. I even thought about using the Velociraptor binary parser to do it. But in the end, I wanted to also pull the logs out of memory. And the Microsoft article referenced an old tool from Matt Graeber called TCG Log Tools. So we can click here and open it up. And this is really handy. So when I played with it, it's fairly verbose, the output. But what I've done is essentially deplete it using the Velociraptor. Let me just show the artifact. Using the Velociraptor tools infrastructure. So we'll hit edit. And you can see we have kind of two components. One is Matt's module here, right? So this is a PowerShell module that we throw into the tools component. And then I have an execution script that I'm running in my gist online. And the reason for that is when we import a PowerShell module, we need to actually .source it, right? So it was very difficult to pass the required parameters across. So what I wanted to do was import the module here and then run the module. And you can see the settings that I'm running here. Now you can change this, and at the moment I'm outputting a minimal cert output. It will just return the digest hashes, but you can output all information, which was extremely large for all of the the certificates associated with TCG, sorry. And then I'm converting to JSON at a depth of 8. In terms of the artifact itself, you can kind of see we have our two tools running. We're then calling PowerShell and looking at the script. And I think a lot of people like to run PowerShell in Velociraptor, and they'll try to put the script here directly and just run it in memory. But one of the problems is when you're running a tool like this, it's so large that this exe CVE capability has a limit in characters, and I think it's 1,000 or 2,000. But in any case, with a large script, I don't try anymore. I just initially do this kind of use case. Here, the length, I've just added a stupidly large number. So essentially, it will concatenate all the lines together. And then I join the output and then parse it with parse XML, right? We have a couple of kind of presentation things as well at the end. So let's run that, and I'll show you kind of what that does. So down to collection, boot application. I don't think there's any parameters, or maybe there is. You can see it, it's pointing at logs. We'll select this for this use case, but the thing to point out is when you're hunting, all parse logs returns a lot of information. So don't run it across thousands of machines. I've run this as a hunt across thousands of machines, and it's really interesting looking at the data points you pull out. But what this will do is it will pull out the measure boot logs and parse them, but it will also extract logs from memory. And that's the main reason why I wanted to use Matt's tool, because he essentially uses an API that lets us extract out of memory. So it was a really quick and efficient way for me to deploy this capability in terms of me, instead of me building out a specific Velociraptor plugin for it. It just wasn't really feasible to spend the day or however long it would take me to write the plugin. It was much simpler to spend a couple of hours and just get this working. So you can see the results when it comes back. You can see in the artifact, I have at the bottom, I have some, and you can't see it here, but if we go to boot application, the presentation things that I was referencing, these are essentially VQL templates in Notebook. So they automatically populate. And it just makes your triage a little bit easier when you add little helpers like this into your VQL. So they're not in results. You've just got the raw data here. But in your VQL, this is like a data stack of these results. And you can see this is the one that's running, and there's two of them, and one is because one's on disk and one is in memory. And this is the normal boot application, right? So this is super easy to spot the evil in an EFI boot like this. And then below I've got the raw information. So you might be interested in what the raw data is like. You can see here, you've got the file, the header, and there's not a huge amount of useful information here, but essentially PCR4 is where the boot info happens, and you can bounce down. Digest is like the cert info. You can read more on Matt's site and the documentation that I've linked if you're interested in that. But you see you can bounce down. So what we're doing is we're pulling out all of these entries, these media device paths. And when you read the documentation, you can actually get a lot of information out of the boot process. And that's why it's an interesting triage action, because when I've ran this across lots and lots of machines, you find a whole bunch of different vendors have EFI kind of boot things happening. And it's interesting to jump in and kind of see what's happening during an EFI boot. Okay, so the next one we're going to look at is the registry. And for that, I think in this particular install, on my machine anyway, I didn't have the registry key. And what BlackLotus does is it will check for this key and it will set it at 0 if it's there. And essentially, this is a configuration that says, hey, have enforced integrity. So if I jump in and create a new PowerShell, and you can see all we're doing is just adding the registry key for this, just to test the detection, nothing really flash. But this is often how I do detection use cases, right? Is often you might find something in IR and you're very quick to do detection. But if you don't have an IR, or if you're just doing lab work, you do need to generate data. So now we've generated the data, we can come into here and rock out the Windows registry, HVCI. Now, obviously, all of these are on the exchange. And you can see the glob. So this is exactly what we were working on before. This only shows 0. This isn't important for this use case when I'm running it here because it's just one machine. But when you're hunting and running this across many, many machines, select that and it will only show the entries that are 0. Otherwise, it will return all the ones as well. Alternatively, just run it and then in your notebook, you can configure that to show what you're interested in. And you can see, look, boom, presentation's nice. We can hunt for the piece that Microsoft are referencing. Okay, so the next is the event logs. And there are a couple of event logs. And to be honest, I think these are a little bit weaker use cases than the others. The reason is this top one seems okay, but they're just error messages in Defender. Now, what was interesting, or what is interesting about BlackLotus, is that it messes with the token privileges of Defender. And when I just ran EVTX Hunter on the endpoint, I saw a bunch of these similar errors, Service Control Manager 7023s for other services as well. So it made me think maybe it's messing with, a higher level than just Defender, and it's breaking a few things. In any case, I guess it shows that you should be following up errors, right? So actually, let's go back and I'll copy paste this just to make our lives easier. And most people know about EVTX Hunter nowadays, I think. In any case, this is an artifact that I wrote exactly for this use case to help kind of grep through event logs. And this is, like, I didn't really cover event logs in the performance stuff, but this is a big performance improver where by targeting, and you can see using Defender star, this glob, it's loose enough to catch any event log that has Defender in it, and it will hit this one. But it's also targeting and will be very, very fast as well. So the event ID we're interested in is this. So ID regex, and you can do like a strict regex or you can keep it loose. It doesn't matter in this case. And what we're interested in is any of these IDs that are referenced in the Microsoft article. And of course, remove the whitelist because we don't want to accidentally whitelist stuff out. So when we run that, we should get some results back. And you can see we've got 8 results. And you can see these are all for errors in Defender. Interesting stuff. Similarly, we can do this next one, which is just looking at the system event log. and looking for this error. And this is the one that I thought was a bit, yeah, not super valuable, but you know, you can always hunt for it, I guess, if you're bored. I just think this one is probably going to be noisy. One thing about the Microsoft article is I think they may have used Defender as their keyword, but my service was called WinDefend. So always be aware of that. Like the Microsoft article is awesome, but you know they're obviously going off a machine that they're using in their lab, and not, was it 7023? They're going off a machine that's in their lab, and it may be different for you. So don't even trust what I'm giving you, right? That's why I try to make all of these items configurable. So when you're running your detection use cases, you can run things and validate, but you can also change. And ideally, if you find something that is better or something that's messed up, submit a pull request and we'll add it into the project. So when we run this, you can see we've got a single row and we've got WinDefend, the service terminating. Really cool. Like I said, I'd probably leave this one off unless you're able to baseline it before. But it's really good to know that this capability exists. This is extremely targeted because we said, hey, look at the system log, look for a specific event ID, and it's blistering fast. So the only thing we might want to add now is maybe just run the services. And if we look at Windows services, so this one here, and then we target Defender, display name equals Defender. Just make it really easy, right? And this should return back our running service. So there is an avenue for potential follow-up where we might want to maybe look at a service that's running and one of these errors that we experienced. But for me, I'm pretty happy with the other detection. If anyone wants to kind of add to the lab and have a go at that, like a combined artifact that checks both, I think that would be an interesting detection to add to this, even if you look at adding maybe some other AV products as well. Like, is the service running? And then is there any errors associated with that as well that may indicate something might be messing? Thank you. That's really it. And I hope you've enjoyed the Velociraptor workshop.